Hi, I am Margarita Metaxa, NOC for Greece. Thank you for the opportunity being part of this prestigious workshop. Today, I'm going to share with you a journey in space exploration through the educational program we implement in Arsakeio School in Greece since 2023. The information will be quite rich, yet still not covering all done, but the educational value and transformative potential will be obvious. Exploration is a driving force within humans. We have an innate desire to discover, to understand the world around us, and learn through the experience gained. How different could the course of history for humanity have been without the great explorers and seafarers who, through their daring missions, opened new routes and with them the next chapter of humanity, bringing new resources, new scientific knowledge, and shaping new societies? Today, space explorers have taken up the torch, continuing their quest across the cosmic oceans, the vastest and most mysterious realms that surround us. I will present you directly the activities we conduct so to understand their pedagogical and scientific background directly. For the introduction, we used a bingo game with all the necessary information about space programs. Then, students explore a platform of NASA where space technology can be found in our everyday life. We ask our students to design and construct with simple, low-cost, everyday material the Orion crew capsule under constraints about size and weight, with the challenge to land without overturning, falling from 1 meter. Then our students went through coding and make a 3D model of SLS and present it in science fairs. Finally, they built their own launch system and launched their paper rockets using tracker. They measure their trajectories. For the main course, we select 3 specific educational guides created by NASA for the Artemis project. We adapted, modified them for the Greek educational system, and started the explorations. Students of the second class of gymnasium select the appropriate human landing site of the moon in between 5 possible sites using NASA topographic maps and data. Considering different resources and conditions, students weighed benefits versus risk for the selection. They took in account temperatures, inclinations, concentration of hydrogen, height, and they decided. Then they design a scale replica of the landing site, make a 3D model of it, and finally, they are challenged to work to design and construct a model of lunar lander that uses the thrust of a balloon to slow the rate of descent. The goal is to slow the rates of descent as much as possible for simulating a soft landing after dropping the lander from 1 and 2 meters high with and without propulsion. Students of the third class of gymnasium act as NASA researchers to mitigate the top crew risk in space. Dealing with radiation exposure, students have to experiment with different shields for their astronaut potatoes upon their choice under conditions and restrictions. Then they bake them in conventional ovens and measure their internal temperatures, deciding for the most effective silt. Additionally, they are challenged after designing to construct and build a device to counter bone loss and muscle atrophy in different gravity using knowledge of skeleton system osteoporosis and present it hypothetically to NASA. Deep space communication is chosen for the first exam. Students went through concepts of communication, signal delay, latency, and network. They measure the speed of light in microwave ovens with marshmallows. They built a model of Earth, Sun, Mars, understanding distance variation, explain Mars launch window, and calculating signal delay times. They encode, decode messages from binary to hexadecimals. They create protocols and network routing solutions like minimum spanning trees. For the closure, students reflect on Earth's unique ability to host life. Through two experiments we created, the first, Space Gardening, is already hosted in the electronic Astro-Edu journal of IAU. There, students construct their own plant growth jumpers from shoeboxes and conclude that successful cultivation in space requires carefully controlled conditions, specific light spectrum and intensity, optimal temperature, and compensating of the absence of gravity. These reveal both challenges and the vast potential of space agriculture for long-term missions. Finally, students experiment with tardigrades. TARDIS, these fascinating water appears combining elements of science fiction with real scientific data and analysis. Students collect tardigrades from moss, separate them, take a look at them through the microscope, then they dehydrate them and test their survival under extreme conditions of salinity, temperature, and pH. After that, they hydrate them and return them in their home moss. All activities are based on collaboration, inquiry, defined criteria, and creative constraints. Students in teams reflect the lessons and insights gained through the inspiring educational experience following the scientific process or the engineering design process. We can certainly conclude that space education is an excellent STEAM-based gateway that uses space exploration and astronomy as a powerful catalyst for creative innovation and interdisciplinary learning, enabling students to think, design, and act as true explorers of knowledge. Thank you for your attention.